About 4.5 billion years ago, our solar system did not exist. There was no sun, no planets, no Earth. Only a vast, cold cloud of interstellar gas and dust, drifting silently through space. Then, gravity took hold. That cloud collapsed inward, spinning faster as it flattened into a wide disk of matter. At its center, pressure and temperature climbed higher and higher until the conditions became extreme. Hydrogen fused into helium, and our sun was born. Around this newborn star, the remaining material in the disk began to change. Dust grains collided, stuck together, grew. Over time, these clumps became larger, heavier, more spherical. They were the building blocks of planets and moons. Far from the sun, where temperatures were low, these growing worlds were rich in ice, liquids, and gases. Closer in, where heat dominated, only rock and metal could survive. That is where Earth formed. Not gently, not peacefully, but through constant collision, heat, and violence. Early in its existence, Earth was struck by a Mars-sized world called Theia. The impact was catastrophic, powerful enough to tear material away from the young planet. That debris did not fall back. It gathered in orbit, it cooled, and over time, it became the moon. What follows is not a timeline, it's an experience. I'm going to spend one full day inside each major stage of Earth's history, standing on the surface as it changes, waiting as the planet decides what it wants to become. Sometimes that day will behave the way we expect, sometimes it won't. And the first place I arrive is a world that has only just begun to exist. The first eon has a name, Hadean, named after Hades, the Greek god of the underworld, not because this place was evil, but because nothing living could survive here. About 4.5 billion years ago, this was the entire planet. No continents, no oceans, no stable ground. The surface beneath my feet looks solid only at a distance. Up close, it's a skin-thin, fractured, unreliable. In some places, it holds enough to stand. In others, it splits open without warning, revealing slow-moving fire beneath. This isn't a world with lava flows. It's a world where the floor is lava, interrupted only briefly by crust that hasn't yet decided to stay solid. The planet is still cooling. The sky above me has weight, not clouds. Haze, ash, gas. Light doesn't arrive cleanly here. It scatters through a thick atmosphere, dominated by carbon dioxide, trapping heat close to the surface. The sun itself feels weaker than it should be, dimmer, and yet everything burns. That contradiction defines this place. Heat radiates constantly from the ground. Even where nothing glows, warmth seeps upward through stone. Standing still is uncomfortable. Standing too long is worse. Nothing rests here. Impacts still happen. Not endlessly, not rhythmically, just often enough. Some arrive as distant flashes on the horizon. Others announce themselves only through the ground, a deep physical jolt that travels through stone before sound ever follows. This isn't chaos. This is normal. This is what stability looks like at the beginning. I wait. Time should stretch here. It doesn't. The light shifts too quickly. Darkness returns before my body is ready for it. At first, I think I'm misjudging it. Then I understand. This planet spins faster than it ever will again. A single day here lasts only a few hours, roughly 6 at most. There's no way to spend 24 hours in one place when the planet itself refuses to slow down. There is no single day here. Light comes and goes again and again. The rule breaks here, not because I choose it to, but because the planet does. Between those brief days, nothing improves. The surface breaks, reseals, then breaks again. Heat escapes, then builds back up. The sky shifts in color and brightness, but never clears. Time here doesn't reward patience. And yet, something about this place doesn't match the image people usually imagine. Because buried inside some of this rock, sealed away for billions of years, are tiny mineral crystals, zircons. They're small, easy to overlook, but they carry a quiet implication. These minerals could only have formed if liquid water existed here, at least briefly. Not oceans, not rivers, but water touching the surface long enough to leave a trace. Standing here, that feels impossible. Everything I can see argues against it. The heat, the instability, the constant recycling of the surface. And yet, the evidence exists. Maybe rain fell, briefly, before flashing back into vapor. Maybe steam condensed for moments before the ground swallowed it again. Not enough to transform the planet, not enough to last, just enough to leave proof. That changes how this place feels. This isn't a dead world, it's an unfinished one. A planet swinging violently between extremes, impact and calm, melting and cooling, over and over again, without memory and without intention. If life were to appear here, I would never notice it. It would be microscopic, ephemeral, erased almost instantly. This planet isn't waiting for life. Life will have to wait for the planet. The surface holds slightly longer than it did before. Glowing fractures seal more often than they open. The heat still dominates, but it loosens its grip just a little. Change is happening, but not on any schedule that recognizes witnesses. When the pull comes, it's abrupt. No warning, no resolution. The unfinished ground, the heavy sky, the constant heat, all of it vanishes at once. The planet continues cooling without me. When I arrive this time, the planet feels different. Not calm, not safe, but quieter. This eon begins around 4 billion years ago, and for the first time, the surface doesn't immediately betray itself. The ground holds. It still fractures, still glows in places, but it no longer feels like it's about to melt out from under me at any moment. Earth is cooling, slowly, unevenly, but enough to change everything. The sky is still heavy, still thick with gases that trap heat close to the surface. Carbon dioxide dominates, wrapping the planet in warmth. Light reaches the ground more consistently now, even if it's still filtered and dull. And then the rain begins. Not a storm, not a season. Rain that lasts for millions of years. Water falls, evaporates, and falls again, over and over. It collects in low places, then spreads outward as the surface reshapes itself. Basins fill. Depressions deepen. Eventually, the water stops disappearing. Oceans begin to form. They don't arrive all at once. They creep across the planet slowly, swallowing vast stretches of land until water becomes the dominant feature of the surface. From where I stand, the horizon no longer glows red. It reflects. This is the first time Earth feels covered instead of exposed. Somewhere in these waters, something new enters the stage. Not visibly, not dramatically. Life. The first cells appear. Simple, microscopic, fragile. They don't announce themselves. They don't change the landscape in ways I can see from here. They simply exist. and spread. If I didn't know what to look for, I would miss them entirely. They drift in the oceans, they cling to surfaces, they multiply slowly, quietly, without intention. There are no plants, no animals, no movement that catches the eye. And yet, this is the most important change the planet has ever undergone. For the first time, Earth is no longer lifeless. I stand at the edge of the water for a long time. The surface is dark, broken only by subtle textures where chemistry and heat still interact. In the shallows, the colors don't look the way I expect them to. Not blue, not green. Some scientists believe that at this stage, parts of the planet may have carried a faint purplish tint, not across the entire world, but in patches. Microbial communities may have used pigments different from those we're familiar with today, absorbing light in unusual ways. It's only a possibility. The evidence is indirect. The debate is ongoing. But standing here, watching the light interact with the water, it doesn't feel impossible. This planet is still experimenting. Days pass, longer than before, but still unfamiliar. The rhythm of light and darkness is settling, slowly, stretching towards something recognizable. The oceans continue to spread. The surface continues to cool. Life continues to multiply, unseen and uncelebrated. Nothing dramatic happens while I'm here. No explosions of complexity, no sudden transformation. Just persistence. That may be the most alien thing of all. Life doesn't conquer the planet. It doesn't reshape it yet. It simply refuses to disappear. When the pull comes, it's gentler this time. The water remains. The sky remains heavy. And somewhere beneath the surface, life continues, whether I'm here to witness it or not. When I arrived this time, there is almost nowhere to stand. Most of the planet is underwater now. The oceans don't feel temporary anymore. They stretch outward in every direction, broken only by scattered fragments of land that rise briefly above the surface before disappearing again. Beneath all this water, something slow and heavy is happening. The first supercontinents are beginning to take shape, not at the surface, but far below it. Massive blocks of crust pressed together in the depths, unseen, unfinished, their outlines only hinted at by subtle changes in the seafloor above. Earth is still building itself from the inside. The rhythm of the planet feels faster. Light and darkness trade places more quickly than I expect. The sun rises, falls, and rises again before my sense of time can settle. The planet is still spinning faster than it ever will in the future. Days are shorter here. The world hasn't learned how to slow down yet. And as I stand here watching these quick cycles pass, it hits me. I've now witnessed 1 billion years of this planet's history. Life is no longer a question here. It's present. Not visible in motion, not recognizable as anything familiar, but it leaves marks. Along shallow coastlines and in warm, sunlit waters, layered structures slowly form. Thin, uneven buildups created by microscopic organisms living together, growing upward grain by grain. Stromatolites. They don't move. They don't compete. They simply persist. Layer upon layer, they trap sediments, turning soft material into stone. Long after the organisms themselves vanish, the structures remain, preserved as some of the earliest physical evidence that life existed here at all. I'm standing beside proof, and life is no longer just surviving. It's beginning to use the sun. Some of these microorganisms are learning how to capture light and turn it into energy, not efficiently, not safely, but effectively enough to matter. Photosynthesis may have begun as early as this. If so, the consequences are enormous, even if nothing looks different yet. The atmosphere hasn't changed, the oceans haven't reacted, but a process has started that will eventually reshape the entire planet. Right now, it's quiet. As the short days continue to pass, the oceans remain dominant. The continents continue forming out of sight. The sun continues to rise and fall too quickly, and life continues doing what it does best, staying. When I'm pulled away, the water doesn't retreat. The stromatolites keep growing, the planet keeps turning, and the sun keeps feeding something that doesn't yet understand what it's about to change. Around 3.2 billion years ago, in the Mesoarchean, the planet starts to organize itself, not at the surface, but underneath. The oceans are everywhere. They cover most of the planet now, pressing down on a crust that's still thin, still young, still flexible. Below that surface, the ground is no longer drifting aimlessly. Huge slabs of the planet are moving. They collide, buckle, and force one another downward. Some are pushed deep into the interior, where they soften, break apart, and disappear back into the planet they came from. This is the beginning of continents. Not the shapes we recognize today, but the process that will eventually create them. Earth is recycling itself. The oceans here are not comforting. They're hot, uncomfortably so. Warm enough that standing near them feels like leaning over a steaming bath, except this heat never fades. In places, water temperatures climb above 40 degrees Celsius, making the oceans feel less like refuge and more like stress. And yet, life thrives here. Microbes are everywhere. They spread across the seafloor, float through the water, cling to surfaces wherever chemistry and heat allow it. There are no plants yet, nothing to slow the buildup of greenhouse gases, nothing to regulate the atmosphere. Heat accumulates. The sky traps it. Carbon dioxide dominates the air, locking warmth and place. With no oxygen present, nothing here is breathable. This atmosphere isn't hostile in a dramatic way. It's simply incompatible. If this were a true arrival, if staying were possible, survival wouldn't even be a question. It would end immediately. But life doesn't need comfort. It doesn't need cool temperatures or clear skies. It adapts. While the planet overheats, microbes continue expanding into every available niche. They don't change the world yet. They don't control it. They endure it. Above them, the continents are still being written, crushed together, torn apart, and reshaped again and again, laying the foundations for land that won't fully emerge for hundreds of millions of years. This era doesn't feel dramatic. It feels busy. The planet is working, and it doesn't pause. The plates continue moving. The oceans stay hot. Life keeps spreading into places nothing else could tolerate. This era begins around 2.8 billion years ago, and for the first time, the planet feels connected. Not quieter, not calmer, but coordinated. The surface still belongs mostly to the oceans, but the land beneath them is no longer acting in isolation. The slow movements that began earlier now stretch farther and last longer. Plates collide, separate, and collide again. Not randomly, but as part of a growing system. Earth is mixing itself. Material from deep inside the planet is carried upward. Surface material is dragged back down. Heat, minerals, and chemistry circulate through loops that didn't exist before. The planet is no longer improvising. It's developing patterns. Life responds immediately. Single-celled organisms are no longer scattered or rare. Simple life forms, prokaryotes, similar to modern bacteria, spread across the planet's oceans and shallow regions. They colonize every environment that allows it, Warm waters, mineral-rich surfaces, places where chemistry and light overlap. Life is still microscopic, still silent, but it is everywhere. The atmosphere, however, remains unchanged. There's still no oxygen here. Nothing in the air would support complex organisms. Greenhouse gases continue to trap heat, keeping the planet warm and unstable, though no longer chaotic. This world is learning balance. Imperfectly, slowly. Time feels different again. Days are still shorter than anything familiar, but they're lengthening. Light lingers longer. Darkness waits. The planet is easing toward a rhythm that doesn't exhaust itself as quickly as before. Along the edges of the oceans, microbial communities spread into wide mats, coating the seafloor and shorelines. They don't move. They don't compete in ways I can see. They persist. Some of them are quietly altering the chemistry around them. Not enough to change the sky yet, not enough to announce themselves, but enough to matter later. This era doesn't feel dramatic. It feels busy. The planet settles into habits. Life becomes dependable. Geology becomes organized. For the first time, Earth feels less like a series of accidents and more like a system. The oceans remain full. The plates continue moving. Life keeps multiplying beyond sight. And somewhere within this growing balance, the conditions for a permanent transformation are quietly forming, one that will soon change the air itself. We are now in the Siderian, about 2.5 billion years ago. At first, nothing looks different. The oceans are still dark and heavy. The land is still sparse. Life remains small, simple, easy to miss. But something fundamental has begun. This period will later be known as the Great Oxidation Event. For a long time, life here took energy quietly. It fed on chemistry, on heat, on whatever reactions the planet allowed. Now, some organisms have learned something new. They are learning how to use light, not just to survive, but to split molecules. In the shallow waters, vast colonies of cyanobacteria spread across sunlit regions. As they absorb sunlight, they release a byproduct they don't need: oxygen. It isn't released gently, it's expelled, almost like a metabolic reflex. At first, it changes nothing. The oxygen doesn't rise into the air, it doesn't build up. It's immediately consumed by iron dissolved in the oceans, by volcanic gases, by the surface itself. The planet absorbs it all. For millions of years, this continues. Life produces oxygen, Earth erases it. The oceans begin to change color. Iron that once flowed freely through the water reacts, falls out of solution, and settles on the seafloor in massive layers. The water slowly clears in places, but what's happening below is more important than what I can see. The planet is paying off its oxygen debt. Only when those sinks begin to fill does something unprecedented happen. The oxygen doesn't disappear, it accumulates. Slowly at first, then unmistakably. The sky begins to change. Not to blue, not yet, but away from what it was. The atmosphere, once dominated by greenhouse gases, starts to lose its grip on heat. Oxygen reacts with methane, stripping it from the air. The planet cools. Ice spreads across the surface and remains there, not for seasons, not for centuries, but for millions of years. These are some of the longest ice ages the planet has ever experienced. This isn't progress, it's catastrophe. Most life on Earth cannot tolerate oxygen. To them, it's toxic. What they created as waste becomes a weapon. Entire ecosystems collapse. Countless organisms vanish without ceremony. This is one of the first mass extinctions in Earth's history. It doesn't arrive as an impact. It doesn't arrive as fire. It arrives as air. The planet doesn't care. It keeps changing. As the cold persists, something else becomes clear. By now, we've witnessed nearly 2 billion years of this planet's history together, and Earth is no longer the world we started on. Some organisms survive the oxygen. A few adapt to it. A new metabolism quietly emerges, far more efficient than anything before it. The atmosphere will never return to what it was. From here on, the rules are different. The planet has chosen a side, and it didn't ask permission. When this era ends, Earth is no longer just a warm microbial world. It's a planet with an atmosphere that can change life forever. And it has only just begun to learn what oxygen can do. We enter the Rhyacian, a little past 2.3 billion years ago. The oxygen hasn't gone away, and because of that, the cold doesn't either. Glaciers creep outward from the poles, then from latitudes that should never freeze. Eventually, the ice reaches the oceans. Then it goes farther. From where I stand, the world looks muted. Color drains away. The surface reflects light instead of absorbing it. Sunlight strikes ice and bounces back into space, leaving less heat behind with every passing cycle. This isn't a single winter. It's a planet locked into cold for millions of years. In places, the oceans freeze at the surface, sealing liquid water beneath thick layers of ice. The planet doesn't stop moving. Tectonic plates still shift, volcanoes still erupt, but all of it happens under a frozen skin. The atmosphere remains thin and harsh. Oxygen exists now, but not in abundance. Not enough to make this world gentle. Methane is largely gone, stripped away by the same oxygen that made this transformation possible. The greenhouse blanket is torn. Earth struggles to warm itself. Life retreats. Not everywhere, but almost. Anything that cannot tolerate the cold disappears. Vast stretches of the planet become uninhabitable. Survival narrows to refuges. Pockets of liquid water beneath ice, warm zones near volcanic activity, places where chemistry and heat still overlap. Life doesn't flourish here. It hides. I wait, and nothing dramatic happens. That's the cruelty of this era. No explosions, no sudden collapses, just endurance. The ice stays. The cold persists. The planet holds its breath. But deep beneath the frozen surface, something continues quietly. Volcanoes keep releasing gases. Carbon dioxide accumulates slowly in the atmosphere because ice and rock can no longer absorb it efficiently. Over immense spans of time, heat begins to build again. The planet is preparing to thaw itself. When the ice finally loosens its grip, it won't be subtle. The release will be violent. Meltwater, flooding, chemical chaos. But that moment is still far ahead. For now, Earth remains locked in white. Life survives barely, proving something new about itself. It doesn't just adapt to change, it can outlast it. We are now in the Orosirian, beginning around 2.05 billion years ago. The ice is loosening its grip. Not all at once, not everywhere, but the planet is warming again. The frozen surface fractures and retreats. Meltwater floods across land that hasn't seen liquid water in millions of years. Oceans reconnect. Chemistry surges back into motion. Earth is waking up. The atmosphere is different now. Oxygen is no longer a brief visitor, it's a permanent presence. Still scarce, still dangerous to many forms of life, but no longer erasable. The planet remembers this change. And then, without warning, it struck. A massive object collides with Earth in what is now southern Africa, carving out a scar that will survive for billions of years. Today, we know this remnant as the Rhyacian Dome, the largest and oldest confirmed impact structure on the planet. The planet absorbs the blow. Dust fills the air, shockwaves travel through crust and ocean alike. Whatever fragile stability existed is disrupted again, not by ice this time, but by force. And then, as always, Earth recovers. This era is marked by building, not life, but land itself. Some of the earliest long-lived continental cores begin to rise. Ancient land masses take shape, pushing upward into mountain ranges that rival anything the planet has formed so far. These aren't mountains meant to last. Erosion begins almost immediately. Wind, rain, and gravity grind them down, recycling their material back into the oceans. But for the first time, land is becoming persistent. The continents are no longer just forming and vanishing, they're staying. Life responds cautiously. Oxygen-tolerant organisms expand into new environments opened by changing chemistry. Ecosystems re-establish themselves after the cold, after the impact, after the chaos. Nothing rushes. Evolution here is quiet, but it's no longer fragile in the same way. The planet feels heavier now, not in weight, but in memory. It carries scars, layers, history that doesn't reset every few 100 million years. By the end of this era, Earth is no longer recovering from catastrophe. It's stabilizing. Slowly, imperfectly, but enough that the next changes won't erase everything that came before. Around 1.8 billion years ago, Earth enters the Statherian, a long pause in the planet's violence. At first, this era feels calm, too calm. The planet doesn't collapse, it locks in. The chaos fades, the oceans hold their ground, the climate steadies, and the atmosphere stops swinging between extremes. Earth appears composed. Beneath that calm, something massive has taken shape. The continents are no longer scattered fragments. They've drawn together into one of Earth's earliest true supercontinents, Columbia. Vast stretches of land are now connected, forming a single dominant mass surrounded by global oceans. For the first time, the surface feels unified. This changes everything. Weather patterns shift, ocean currents reorganize, erosion intensifies along long coastlines, carrying minerals into the sea in quantities never seen before. The planet isn't dramatic here, it's methodical. Life continues, quietly adapting to a world where oxygen no longer disappears. Complex cells still don't exist yet. Everything remains small, microbial, and slow-moving. But something happens during this era that should not happen. Not naturally. Deep within the crust, in what is now Central Africa, uranium-rich deposits accumulate under just the right conditions. Water moves through the rock, slowing neutrons. Reactions begin. For a brief moment in Earth's deep past, the planet runs a nuclear reactor on its own. Not a weapon, not a catastrophe, a natural process. Today, its remains are preserved in what we now call the Oklo Natural Nuclear Reactor, proof that the chemistry of this era crossed thresholds we rarely imagine. The reaction doesn't last forever. It starts, it runs, it shuts itself down, and the planet carries on, indifferent to how strange that moment truly was. Above ground, erosion continues its slow work. Mountains wear down, sediment spreads across shallow seas, the continents flatten, broadening into stable platforms. Earth feels older now, not ancient, shaped by what it survived. By the end of the Statherian, the planet is no longer defined by constant crisis. It has learned how to maintain itself for long periods of time. That stability won't last forever, but it will last long enough for something entirely new to emerge. By about 1.6 billion years ago, during the Calymmian, the planet has grown quiet. From the surface, nothing looks dramatic. The continents remain broad and worn down. The oceans stretch wide and quiet. The atmosphere holds steady, no longer swinging wildly between extremes. But beneath that calm, something extraordinary happens. For the first time in Earth's history, cells begin to change internally. Until now, life has been simple, single cells doing everything themselves. Now, a rare event unfolds. One cell absorbs another, and instead of digesting it, keeps it. They cooperate. This merger creates a new kind of life, eukaryotic cells. Cells with internal structures, with compartments, with the beginnings of complexity. This isn't innovation in speed, it's innovation in architecture. Inside these new cells, energy becomes easier to manage. Instructions become easier to protect. Life gains room to experiment without collapsing. Nothing explodes outward yet. There are no animals, no plants, no visible movement. But the ceiling has been raised. The planet itself continues changing. Earth's crust thickens. Continental platforms grow broader and more stable. Shallow seas spread across their edges, creating vast chemical laboratories where nutrients mix slowly, predictably. The oceans remain darker than anything modern eyes would recognize. Light still fades quickly with depth. Most of life remains microscopic, drifting or clinging to surfaces in silence. But now, those organisms are no longer all the same. Some cells are bigger, some are slower, some are more efficient. Life begins to specialize. This era doesn't feel loud, it feels deliberate. Change here is measured in structure, not survival. Nothing is wiped out, nothing is forced to adapt overnight. Instead, life quietly acquires the tools it will need much later. By the end of the Calymmian, Earth looks almost unchanged on the outside. But internally, life is no longer trapped in simplicity. It has learned how to build inward. And with this moment, we've now witnessed nearly 3 billion years of Earth's history together. By around 1.4 billion years ago, during the Ectasian, Earth settles into one of the most stable stretches of its entire history. On the surface, almost nothing seems to happen. The continents remain low and worn. The oceans spread calmly across the planet. The atmosphere holds steady, no longer prone to violent shifts. For long spans of time, Earth feels paused. But deep below the surface, the planet is still evolving. At the very center of Earth, pressures and temperatures reach a tipping point. Molten metal begins to behave differently. Slowly, imperceptibly, the inner core starts to crystallize, iron aligning into solid form at the heart of the planet. This process is invisible from above, but it matters. As the inner core grows, it strengthens Earth's magnetic field. The planet becomes better protected from solar radiation, better at holding on to its atmosphere. Earth is quietly reinforcing itself. Life continues its slow progress. Eukaryotic cells exist now, but they remain rare and simple. There are no ecosystems to speak of, no food chains, no visible competition. Most life drifts through the oceans or clings to surfaces, living out long, uneventful generations. Evolution here is slow by design. Change doesn't come from pressure, it comes from time. The oceans remain dark and heavy. Light still fades quickly below the surface. Nutrients circulate slowly through shallow seas and continental shelves, feeding microbial communities that expand, contract, and persist without drama. Nothing is rushing, nothing is collapsing. This era doesn't announce its importance, it hides it. For hundreds of millions of years, Earth holds steady, continents barely shifting, climates barely changing, life barely experimenting. But this long stillness is not wasted, it's preparation. The planet is stabilizing its core, its magnetic shield is strengthening. Life is learning how to exist without constant catastrophe. By the end of the Ectasian, Earth is no longer fragile, it's resilient. And that resilience will soon allow life to attempt something far more ambitious than survival. By around 1.2 billion years ago, during the Stenian, something subtle but revolutionary begins. The planet still looks familiar. Continents remain low and eroded. Shallow seas spread across their edges. The climate holds steady, protected by a strengthening magnetic field and an atmosphere that no longer collapses under stress. Earth feels dependable now. Life has had time. And then, quietly, reproduction changes. Until now, life has copied itself by splitting in two, passing on the same instructions over and over again. In this era, some organisms begin doing something different. They mix. Genetic material is exchanged, shuffled, recombined. Errors are no longer just mistakes, they become possibilities. This is the beginning of sexual reproduction. Fossils from this time, including early algae like Bangimorpha, show patterns that suggest this new strategy, one that allows life to adapt not just slowly, but flexibly. Variation accelerates, not in size, not in strength, in potential. The oceans remain dark, but life within them is becoming more diverse. Cells specialize further, some grow larger, some live longer. Some form simple multicellular arrangements, sticking together instead of drifting alone. Nothing here resembles animals yet, but cooperation is no longer rare. The planet continues its steady rhythm. Tectonic plates move slowly. Continents drift and rearrange at a patient pace. Chemistry cycles predictably through air, rock, and water. This stability matters. It gives life space to experiment without being erased. By the end of the Stenian, Earth hasn't changed much on the outside, but internally, life has unlocked a new engine. Evolution is no longer limited to copying what already works. It can now explore what might work next. By 1 billion years ago, in the Tonian, the planet appears settled, but tension runs underneath. The surface feels stable. Continents are no longer scattered. They've drawn together into a vast supercontinent, Rodinia, locking much of the planet's land into a single, immense mass. From space, Earth looks organized. From within, it's tense. With so much land clustered together, coastlines shrink. Shallow seas retreat. Nutrients stop spreading evenly through the oceans. Circulation slows. The planet begins to starve its own surface. Life feels the pressure. Nothing collapses immediately. There's no disaster to point to. Instead, ecosystems thin out. Life stops expanding into new forms. Survival becomes about endurance rather than expansion. The oceans remain dark and cold beneath the surface. Light still fades quickly. Life persists mostly where conditions are forgiving, along margins, in sheltered waters, in places where chemistry can still circulate. Above it all, the atmosphere holds steady, too steady. Greenhouse gases continue to build. Weather patterns repeat endlessly. The planet feels locked into a groove, unable to release tension. And then, slowly, the ground begins to move. Rodinia starts to fracture. Cracks open across the supercontinent. Rifts deepen. Magma rises where the crust thins. The landmass that once unified the planet begins to tear itself apart. This doesn't bring relief. It makes things worse. Fresh rock is exposed on a massive scale. Rain and erosion strip it away, pulling carbon dioxide from the atmosphere and locking it into stone. The planet cools, gradually at first, then decisively. Ice creeps outward from the poles. Temperatures drop. Each change begins to reinforce the next. Ice reflects sunlight, cooling the planet further, allowing more ice to form. Earth is slipping. Life doesn't panic, it can't. It adapts where it can and disappears where it can't. Populations shrink. Refuges become everything. The planet has been stable for too long, and now that stability is breaking. Not into chaos, into cold. By the end of the Tonian, Earth is balanced on a knife edge. The mechanisms that once protected life are now pushing it toward a global freeze. The next step won't be gradual. Ice will spread across nearly the entire planet. By about 720 million years ago, the Cryogenian begins, and the planet closes in on itself. Cold isn't arriving anymore, it's already here. Ice stretches far beyond the poles, crawling across continents and oceans alike. What was once seasonal has become permanent. What was once regional is now global. From where I stand, the horizon is white. Not snow, ice. Thick, endless, reflective. The oceans are still there, but they're sealed beneath kilometers of frozen surface. Liquid water survives only in darkness, trapped below, insulated from a sky that no longer offers warmth. The sun rises, but it doesn't help. Light strikes ice and bounces back into space. Almost nothing is absorbed, almost nothing returns as heat. Each day feels the same, dim, cold, unforgiving. Earth has entered a deep freeze. This isn't a single ice age, it's a snowball Earth. Continents disappear beneath ice sheets. Mountain ranges flatten under weight. Glaciers grind slowly, relentlessly, reshaping the surface without ever revealing it. The planet feels silent. Volcanoes still erupt beneath the ice, but their heat is swallowed before it can spread. Tectonic plates still move, but their motion is hidden, buried, muted. Nothing escapes the cold. Life retreats to the few places it can survive. Deep beneath the ice, near volcanic heat, in cracks where seawater still circulates, in isolated pockets where chemistry and warmth barely overlap. There is no expansion here, only survival. Entire branches of life vanish. Those that remain shrink into refuges so small they barely feel real. Generations pass without seeing the surface, without light, without change. Time stretches. The planet doesn't look alive, but it is. Slowly, something begins to shift. Volcanoes keep releasing gases, carbon dioxide that cannot be absorbed by frozen oceans or buried rock. It accumulates in the atmosphere, unnoticed at first. Heat begins to build beneath the ice, trapped, waiting. Pressure mounts. This frozen world isn't stable, it's tense. When the ice finally begins to break, it won't be subtle. It won't melt back into the sea. It will collapse. Floods will surge across continents stripped bare by ice. Oceans will churn with minerals scraped from the land. Chemistry will explode into motion. But for now, the Cryogenian holds. Cold dominates. Ice rules. Life endures, hidden, patient, waiting. By the end of this stay, one thing is clear. Earth hasn't killed life. It's tested how little of the planet life truly needs. By about 635 million years ago, the Ediacaran begins, and the ice lets go. The planet doesn't snap back to life. It exhales. Ice retreats from the continents in slow, uneven waves. Meltwater pours across bare rock, flooding lowlands that haven't seen liquid water in millions of years. Oceans rise. Shorelines redraw themselves again and again. The world feels raw. Freshly exposed rock reacts with air and water, pouring nutrients into the seas. Conditions for life suddenly improve. The oceans turn active, unstable, crowded with possibility. The sky changes too. Oxygen levels rise higher than they've ever been before. Not enough for fire, not enough for comfort, but enough for something new. For the first time, life becomes visible. Not shells, not bones, not teeth or claws. Soft bodies. Strange flattened organisms spread across the seafloor like living impressions. Some look like leaves pressed into sediment. Others resemble discs, fronds or quilted shapes that defy easy comparison. They don't hunt, they don't bite, they don't run, they absorb. Life here lives slowly, feeding directly from the water around it, exchanging chemicals with the environment instead of chasing it. Movement is minimal, defense is non-existent. Predation hasn't arrived yet. The seafloor becomes a living surface. Microbial mats carpet vast areas, and larger organisms rest on top of them, interacting with their environment in ways never seen before. Ecosystems form, not competitive, not violent, but cooperative and fragile. The planet feels unfamiliar again. Continents continue to drift, slowly assembling into new configurations. One of the largest landmasses of this time is Gondwana, stretching across much of the southern hemisphere and reshaping ocean circulation. Climate stabilizes. After the extremes of ice and heat, Earth finds a middle ground. Seasons return. Weather cycles feel predictable. The planet becomes, for the first time, broadly habitable. But this calm is deceptive. These organisms are experiments, not ancestors guaranteed to survive. They lack protection, they lack speed, they lack the ability to respond to sudden threat, and threats are coming. Toward the end of this era, environments begin to change again. Oxygen continues to rise, nutrients fluctuate, the seafloor grows more complex, pressure builds. Some of these soft-bodied forms disappear, others retreat. Very few will cross the boundary ahead. This isn't a beginning that lasts, it's a preview, a quiet rehearsal before conflict enters the story of life. By the end of this stay, one truth stands out. Life no longer hides, it spreads, it experiments openly. And it is about to face competition for the first time. At 539 million years ago, the Cambrian begins and restraint disappears. The planet is recovering. Late Ediacaran ice has retreated. Life that endured the cold steps into newly opened oceans rich with nutrients and stability, and life reacts fast. For the first time, animals actively hunt other animals. Predation appears. That single shift ignites an evolutionary arms race. Eyes become valuable, protection matters, exoskeletons form, movement accelerates, bodies gain direction, symmetry, intent. The oceans erupt with new designs. Early arthropods patrol the seas. Small shelly animals, mollusks, brachiopods, trilobites blanket the seafloor. Some life forms push extremes. Creatures like Hallucigenia test strange shapes and defenses. Many won't last, but they explore what biology can become. Others lay foundations. Early chordates appear, carrying a flexible dorsal cord, the blueprint that will one day lead to vertebrates. Fish-like animals such as Haikuishtes slip through the water, small but transformative. The Cambrian explosion isn't a miracle, it's pressure. Armor leads to stronger jaws. Speed favors sharper senses. Burrowing animals churn sediment, oxygenating the seafloor and reshaping entire ecosystems. The ocean floor is no longer still. It's churned, tracked, scarred. As specialization increases, giants emerge. Predators like Anomalocaris dominate open waters, large, fast, visually advanced. For the first time, the oceans have true apex predators. Life is no longer gentle, but this explosion is unstable. Too many experiments, too much change, too fast. Near the end of the Cambrian, biodiversity drops sharply. Oxygen shifts, climate instability, and possible glaciations or volcanic activity trigger repeated collapses. This isn't a single mass extinction, it's a crash. Many strange forms vanish, whole groups disappear. The Cambrian staircase breaks under its own weight. But the survivors matter. Arthropods, mollusks, early chordates, and echinoderms endure, becoming the framework for the entire Paleozoic era. By the end of the Cambrian, Earth is no longer ruled by passive life. The planet belongs to animals that move, hunt, defend, and compete. And extinction is no longer rare. It's part of how life advances. 485 million years ago marks a turning point, the Ordovician, when the oceans take over. The chaos of the Cambrian has passed. The survivors remain. Life doesn't explode here, it organizes. Most land lies in the southern hemisphere, locked into the vast supercontinent Gondwana. High sea levels flood continental margins, creating warm, shallow oceans that stretch across the planet. These seas are crowded and productive. Reefs expand, shelled animals multiply, filter feeders rise into the water column, food webs deepen, stacking life vertically instead of spreading it flat across the seafloor. For the first time, marine ecosystems feel stable, and something new appears on land. Tiny, simple plants creep onto damp shorelines. They stay low, they rely on moisture, but they exist. The land is no longer completely empty. Back in the oceans, power shifts. Old Cambrian giants fade, new predators take their place. Straight-shelled cephalopods rule the open sea. Early fish appear, armored and jawless. Sea scorpions begin stalking the seafloor. The oceans are alive and dangerous. Even a surge in meteorite impacts around the middle of this era fails to stop diversification. Life adapts, complexity continues rising. For millions of years, the Ordovician feels like success. Then, the planet turns cold. Gondwana drifts toward the South Pole, ice sheets grow, sea levels fall, shallow seas drain away, destroying habitats across the globe. Oxygen drops, ecosystems collapse. This is Earth's first true mass extinction. Nearly 85% of marine species vanish, reefs disappear, entire groups are erased. When the ice finally retreats, the seas return, but the Ordovician world does not. Life survives, thinner, tougher, and changed. "444 million years ago, the Silurian begins, and life regains its balance. The Ordovician extinction has ended. Ice retreats, sea levels rise. The planet settles into a long stretch of warm, stable climate. This is not an era of destruction, it's an era of recovery. The oceans rebuild first, reefs return, marine ecosystems reorganize. Fish diversify rapidly, becoming more common, more varied, and more capable than before. Then, the land changes. Plants begin growing upward. The evolution of vascular tissue allows water and nutrients to move vertically, freeing plants from the ground. Early pioneers like Cooksonia rise above the surface, forming the first forest-like landscapes. The planet gains structure, and towering over these early plants is something unexpected: giant fungi. Massive, trunk-like organisms called prototaxites dominate the land, growing up to 8 meters tall, the largest living organisms on Earth at the time. Before trees rule the world, fungi do. Back in the seas, evolution accelerates again. Fish undergo a major transformation. Movable jaws appear, opening new feeding strategies and driving diversification. Cartilaginous fish, bony fish, and armored fish spread through the oceans. Some fish take a critical step forward. Lobed finned fish develop powerful fins attached to internal skeletal supports, allowing greater control and mobility, a design that will matter later. The oceans grow dangerous. Sea scorpions, eurypterids rise as dominant predators. Some scavenge, others hunt. The largest, Pterogodus, grows up to 3 meters long, becoming an apex predator of the Silurian seas. Life responds by escaping. By the end of the Silurian, the first fully terrestrial animals appear. Millipedes and early arachnids crawl onto land, exploiting a new refuge free from large marine predators. Earth now hosts life in 2 realms: sea and land. The Silurian ends without catastrophe, climate continues warming, tectonic activity increases, ecosystems expand instead of collapsing, recovery is complete, and the planet is ready for its next transformation. 419 million years ago, the oceans change character. This is the Devonian. The planet is warm. Sea levels are high, flooding continental edges and creating vast, shallow seas. The southern hemisphere is still dominated by Gondwana, while warm oceans wrap around much of the globe. These waters are ideal for life, and life responds with force. This becomes an evolutionary arms race, especially between arthropods and fish. Speed, armor, and weapons begin to matter more than ever before. The seafloor changes first. Ancient microbial reefs fade away, replaced by large coral reef systems. A slight cooling of ocean temperatures allows these new reefs to form, rising into complex three-dimensional structures packed with life. The oceans become cities, and cities attract predators. Armored fish, placoderms, rise to dominance. Thick, bony plates protect their bodies. Their jaws are powerful, built not for precision, but for crushing force. At the top of this world swims Dunkleosteus. It is enormous, fast, unchallenged. With one of the strongest bites ever evolved, it rules the open seas. For a time, nothing competes with it. The Devonian Ocean belongs to armor and strength. Life adapts or disappears. Some species grow heavier defenses. Others become faster and more agile. Many retreat into reefs, crevices, or shallow waters where giants cannot easily follow. Evolution accelerates under pressure, but the most important changes are happening quietly, near the edges of water. Lobed-finned fish begin exploring shallow, unstable environments, floodplains, swamps, oxygen-poor pools. Their fins are thick and muscular, connected to internal skeletons. They don't just swim, they push. One of these animals, Tiktaalik, lives at the boundary between water and land. It has fins capable of supporting weight, a neck that can turn, and lungs alongside gills. This is not a fish leaving the water. It is a fish surviving when water disappears. From these forms emerged the first tetrapods, vertebrates with limbs capable of bearing their own weight. They move through flooded forests and muddy margins, not fully terrestrial, but no longer trapped in the sea. This moment reshapes the future. Every land vertebrate, reptiles, birds, mammals, traces its lineage back to the steppe. But the Devonian does not end in triumph. As forests spread across land, weathering accelerates. Nutrients wash into the oceans. Algal blooms expand. Oxygen levels in seawater fall. The seas begin to suffocate. A series of extinction events unfolds, slow, prolonged, devastating. Coral reefs collapse. Many fish groups vanish. The armored giants, including Dunkleosteus, disappear entirely. This is one of Earth's big 5 mass extinctions. Yet not everything is lost. The early tetrapods survive. When the Devonian ends, the oceans are quieter, but the land is no longer empty. Forests stand, animals walk. Life has crossed a boundary it will never cross back. 359 million years ago, Earth enters the Carboniferous. Life fully settles onto land. Forests spread across the planet, not small patches, vast, continuous rainforests. Lowlands flood, swamps dominate. Trees grow tall and dense, dropping enormous amounts of plant material into waterlogged ground. Much of it doesn't decay. Instead, it sinks and accumulates. Carbon is buried. Over time, this will become coal. The atmosphere responds. Oxygen levels rise far higher than today, changing how life functions. Breathing becomes easier. Energy becomes cheaper. Size becomes possible. The oceans recover as well. Marine ecosystems rebound from earlier extinctions. Sharks become dominant predators, streamlined and efficient, controlling open waters as reef systems stabilize again. But the most dramatic changes happen on land. High oxygen allows arthropods to grow much larger than anything alive today. Some scorpions reach the size of small dogs, like Pulmonoscorpius. Millipedes, such as Arthropleura, grow longer than a human is tall, moving slowly through forest undergrowth. This is a world that supports giants. Tetrapods thrive in these humid environments. Early amphibian relatives spread widely, hunting on land but still returning to water to reproduce. Then a critical change appears. Some tetrapods solve a problem no one else has. They reproduce without water. The amniotic egg evolves. Sealed, protected, self-contained, embryos can now develop on dry land. This breaks a dependency that had existed for hundreds of millions of years. Two major lineages split from this point: sauropsids, ancestors of reptiles; synapsids, ancestors of mammals. The future divides here. But the Carboniferous does not remain stable. As forests spread, carbon dioxide is drawn down too efficiently. Global temperatures fall, climates dry, ice sheets grow in the southern hemisphere. Continents collide and merge into Pangaea. The rainforests collapse. Wet environments fragment. Giant insects struggle. Many amphibian lineages decline or disappear. The age of giants fades, but the survivors are different now. Amniotes, especially synapsids, thrive in dry, seasonal environments. They are no longer tied to swamps or constant moisture. By the end of the Carboniferous, Earth is permanently altered. Life dominates land. Reproduction has escaped water, and vast stores of buried carbon lie locked beneath the surface. The planet is ready for a harsher world. $299 million years ago, Earth tightens into a single world. This is the Permian. The continents finish merging into Pangaea. Vast mountain ranges rise. Coastlines shrink. Much of the land now lies far from the sea. The climate dries. Rain shadows form. Deserts spread across the interior. Seasons grow extreme. Large ice sheets still cover parts of the southern continents, forcing sea levels to rise and fall again and again. This is no longer a forgiving planet. It is a selective one. In the oceans, life adapts to instability. Shallow seas fragment into isolated basins. Trilobites persist longer than expected. Goniatite ammonites flourish and diversify, marking time in the fossil record. Sharks evolve into new forms, including hybodonts. Some become strange. One shark, Helicoprion, carries a spiraled, saw-like jaw, a response to unfamiliar prey in changing seas. On land, the Carboniferous giants fade. Oxygen levels drop. Giant insects disappear. Smaller, more efficient arthropods take over. Flies and beetles spread, better suited to dry environments. Amphibians reach their peak, then stall. Large temnospondyls dominate wetlands, but remain tied to water. As climates dry, their future narrows. A different lineage begins to rise. The real winners are the synapsids, stem mammals. They diversify rapidly, filling herbivore and predator roles. Some regulate body heat more effectively. Some chew more efficiently. Some move faster. One becomes iconic. Dimetrodon dominates dry floodplains, its sail helping manage body temperature in an unstable climate. As the Permian continues, synapsids diversify further. Large herbivores feed on tough plants. New therapsids evolve beaks for efficient feeding. Some climb trees. Some glide through the air. Predators evolve alongside them. Cynodonts become small, adaptable hunters. And at the top rise gorgonopsids, saber-toothed predators built to kill large armored prey. For tens of millions of years, synapsids rule the land. Then the planet breaks. In Siberia, massive volcanic eruptions begin. The Siberian traps pour lava across the landscape for hundreds of thousands of years. Greenhouse gases flood the atmosphere. Temperatures spike. Oceans lose oxygen. Acidification spreads. The seas suffocate. This is the Great Dying, the worst extinction in Earth's history. Up to 96% of marine species vanish. Around 70% of land vertebrates disappear. Trilobites go extinct forever. Insects suffer their greatest collapse ever. Forests die back. Apex predators vanish. The world becomes hot, dry, and nearly empty. Only generalists survive. One of them, Lysosaurus, spreads across the planet, becoming the most common land vertebrate for a time. Small cynodonts persist as well, adaptable, unnoticed, waiting. By the end of the Permian, the old world is gone. Life remains, stripped down to what works. 252 million years ago, Earth enters the Triassic, a world rebuilding from collapse. The Great Dying has just ended. Life is thin. Ecosystems are fragile. The planet is hot, dry, and unstable. Nearly all land is still locked together in Pangaea. Vast interiors lie far from the sea. Carbon dioxide levels are high. Oxygen is lower than today. This is a hard world to survive in, and survival favors efficiency. On land, one animal dominates early Triassic ecosystems, Lystrosaurus. Small, tough, and adaptable, it spreads across continents, thriving in environments that would kill most animals. This is not an age of giants. It is an age of endurance. Reptiles diversify rapidly, filling empty niches left behind by extinction. Some return to the water, some glide, some run on upright limbs, conserving energy in the heat. Among them rise the archosaurs, a group defined by efficient lungs, upright posture, and stamina. They include crocodile ancestors, flying reptile ancestors, and something new, dinosaurs. At first, dinosaurs are minor players, small, fast, light-built. Early forms like Colophysis hunt small prey, living alongside larger reptilian predators. They are not dominant yet, but they are built for this world. At the same time, the first true mammals appear, tiny, nocturnal, and hidden. They stay small to avoid competition, surviving in the margins. In the oceans, recovery continues slowly. New marine reptiles evolve, reefs cautiously return, food webs rebuild from scratch. Then, the planet destabilizes again. Toward the end of the Triassic, massive volcanic eruptions erupt as Pangaea begins to split apart. Lava floods the land, greenhouse gases surge, temperatures spike, oceans acidify, ecosystems collapse. This is the end Triassic extinction. Many large reptile competitors vanish, marine groups suffer heavy losses, forests thin. The dinosaurs survive. When the Triassic ends, the world is changed. The supercontinent is breaking, new coastlines are forming, climate patterns are shifting, and the animals best suited for this unstable planet are ready. "201 million years ago, the planet relaxes. This is the Jurassic. The turmoil of the Triassic fades. The supercontinent Pangaea begins to break apart. Long rifts open, new oceans form, coastlines lengthen, moisture returns. The climate becomes warm and humid across much of the world. Rain falls more regularly. Deserts shrink. Forests spread again, thick with conifers, cycads, and ferns. This is a stable planet, and stability changes everything. Dinosaurs take full control. What survived earlier extinctions now expands without serious competition. Dinosaurs spread across every continent, filling nearly every large animal role on land. They grow larger. Long-necked sauropods reach immense sizes, feeding high in forest canopies. Their weight reshapes landscapes, flattening vegetation and opening pathways through forests. Predators respond. Large theropods evolve to hunt giants. Jaws strengthen, teeth lengthen. Power becomes the deciding factor. For the first time, Earth supports land animals weighing tens of tons. The air fills as well. Pterosaurs diversify, dominating the skies. Some are small and agile. Others grow enormous, riding warm air currents above coastlines and seas. And within the forests, something subtle appears. Feathers. Small theropod dinosaurs evolve feathered bodies, first for insulation and display. Near the end of the Jurassic, one lineage crosses a boundary. The first true birds appear. Animals like Archaeopteryx blur the line between dinosaur and bird, carrying teeth, claws, and feathers at once. Flight is no longer exclusive to reptiles. In the oceans, dominance continues. Ichthyosaurs slice through open waters. Plesiosaurs patrol coastal seas. Marine ecosystems are complex and crowded, filled with large predators and fast prey. Life feels abundant everywhere. But not everything thrives. Mammals are present but remain small, mostly nocturnal, mostly hidden. They survive by staying out of the way. The Jurassic is not their time. It belongs to giants. For tens of millions of years, the planet remains unusually calm. No major global extinctions, no dramatic collapses, just expansion. But slow changes are underway. Continents continue drifting apart. Sea levels rise. Climate warms further. The world is preparing for something new. "145 million years ago, Earth looks familiar, but more extreme. This is the Cretaceous. The continents continue drifting apart. Wide oceans open between them. Coastlines stretch longer than ever before. Sea levels rise so high that shallow seas flood deep into continents, splitting landmasses and reshaping climates. There are no permanent ice caps. Even the polar regions are mild. This is a greenhouse Earth. Warm temperatures and abundant rainfall support forests across much of the planet. Vegetation spreads from equator to high latitudes with little interruption. Life thrives in long-term stability. Dinosaurs reach their peak. They dominate every land ecosystem. Enormous plant eaters, fast hunters, armored specialists, herd animals. Food webs are complex and resilient, refined over tens of millions of years. But the most important change is quieter. Flowering plants appear. At first, they are rare, easily overlooked among conifers and ferns. But they reproduce faster, form close partnerships with insects, and evolve chemical defenses. They spread rapidly. Forests change character. Insects diversify alongside them. Pollination becomes a powerful evolutionary force, accelerating change across land ecosystems. Dinosaurs adapt. Some evolve advanced teeth for chewing tough plants. Others develop horns, frills, and crests for display and communication. Feathers become common in many lineages, especially among smaller dinosaurs. Birds diversify, filling the skies in many forms. Mammals are still small, but no longer insignificant. They branch into new lifestyles: climbers, burrowers, swimmers. surviving beneath dinosaur dominance by staying flexible and fast breeding. In the oceans, life flourishes. Warm seas support vast plankton blooms that drive rich food webs. Coral reefs expand. Marine reptiles patrol every level of the water column. For tens of millions of years, the Cretaceous feels successful, stable, productive, crowded. By the very end of the Cretaceous, predators like Tyrannosaurus rex stand at the top of food webs, powerful, specialized, and dependent on a world that feels permanent. Then permanence breaks. An asteroid strikes Earth near what is now Chicxulub. The impact is immediate and global. Shockwaves race around the planet. Wildfires ignite across continents. Dust, ash, and sulfur flood the atmosphere, blocking sunlight. Photosynthesis collapses. Temperatures plunge. Food chains unravel from the bottom up. This is not gradual. It is sudden. Non-avian dinosaurs disappear. Large marine reptiles vanish. Many plant groups collapse. Roughly 3/4 of all species on Earth are lost. The age of dinosaurs ends. But not all life is erased. Birds survive. Small mammals endure. Generalists persist. When the dust finally settles, the world is quieter, but open. 66 million years ago, the world begins again. This is the Paleogene. The asteroid winter has passed. Sunlight returns. Plants grow back. Ecosystems restart. Simplified, fragile, and open. The dominant animals of the past are gone. What remains is opportunity. Mammals step forward. At first, they are small and cautious, but without dinosaurs, ecological barriers vanish. New niches open across the planet. Mammals diversify quickly. Some become runners. Some climb trees. Some dig burrows. Some move toward water. Body sizes increase. Teeth specialize. Senses sharpen. For the first time, mammals become the largest animals on land. Birds expand as well. With flying reptiles gone, birds take over the skies, filling roles as predators, scavengers, and long-distance travelers. The climate shapes everything. Early in the Paleogene, Earth is warm. Forests stretch far toward the poles. Crocodiles and palm trees exist at high latitudes. Then cooling begins. Antarctic ice forms. Ocean circulation shifts. Forests slowly retreat, and more open landscapes appear. Life adapts again. In the oceans, some mammals return to the water. Limbs flatten into flippers, bodies lengthen, and flexible tails begin to drive movement through the water. Nostrils shift upward. The first whales appear. Awkward at first, then fully marine. On land, primates emerge. Small, tree-dwelling mammals with grasping hands and forward-facing eyes. They are not dominant, but they represent a new evolutionary direction. By the end of the Paleogene, Earth feels full again. Mammals dominate land and sea. Birds rule the air. Ecosystems are complex and stable. The planet has recovered, and the modern world is taking shape. 23 million years ago, the Neogene reshapes the planet into something we recognize today. The continents now sit close to their modern positions, and the planet's surface continues to reorganize. Mountain ranges rise higher, including the Himalayas, while a land bridge forms between North and South America, quietly reshaping ocean circulation. As currents shift, the climate responds. The world cools further, ice expands at the poles, seasons sharpen, and rainfall becomes more uneven. Forests begin to retreat, no longer able to dominate every region as conditions dry. In their place, open landscapes spread. Grasslands expand across large parts of the planet, and grasses adapt to life in the open, surviving grazing, fire, and drought. Dense forests gradually give way to wide plains. Life follows. Large grazing mammals diversify. Horses, antelope, elephants, and their relatives, built for speed, endurance, and movement in herds across open ground. Predators evolve alongside them, trading ambush for pursuit. Long legs and stamina become decisive, and ecosystems are reshaped around chase and escape played out over distance. In the oceans, transformation continues. Whales diversify into distinct strategies. Some grow enormous, filtering food from productive seas. Others become active hunters. Along coastlines, seals and sea lions appear, exploiting environments shaped by new currents. Birds adapt as well, thriving in open skies and expanding across continents through long-distance flight. On land, another shift begins quietly. As forests shrink, some primates spend more time on the ground. Upright posture becomes useful. Hands free up. Vision favors distance. The first hominins appear. They are not human yet, but they move differently. They carry objects. They travel farther. Their survival depends less on physical specialization and more on behavior. By the end of the Neogene, Earth feels unmistakably modern. Ice caps exist. Grasslands dominate. Herds roam. Predators chase. And one lineage stands at the edge of something new. About 2.6 million years ago, Earth enters the Quaternary, and the pace of change begins to quicken. The planet cools sharply, and for the first time in its history, climate begins to pulse in cycles. Ice sheets advance across the northern continents, then retreat, only to return again. These glacial rhythms reshape the surface again and again, lowering sea levels, carving valleys, grinding mountains down, and redrawing coastlines with each swing. This is no longer a stable world. It is a world in motion. Life adapts to instability. Large mammals dominate the land, many of them enormous. Mammoths, mastodons, giant ground sloths, and powerful predators built for cold, open environments. Size offers protection, but it is not enough on its own. Survival now depends on flexibility. In Africa, one lineage begins to change in a different way. Early humans evolve not just physically, but behaviorally. They walk upright, freeing their hands. They shape tools. They learn to cooperate, to plan, to pass knowledge forward. Fire becomes a tool. Shelter becomes possible. Memory and culture begin to matter as much as muscle. Over time, this lineage spreads. By the late Quaternary, Homo sapiens appear, physically unremarkable compared to the giants around them, but uniquely adaptable. Humans move across continents with unprecedented speed, adjusting to deserts, forests, coastlines, and ice. Wherever they go, ecosystems change. As the last great ice sheets retreat, the planet enters its current warm interval, the Holocene. The climate stabilizes, rivers settle into place, and humans begin reshaping the land deliberately. Agriculture emerges, villages grow into cities, civilizations rise. All of recorded history, every empire, every invention, every conflict unfolds in what amounts to a geological instant, a moment. Compared to everything that came before, it barely registers. And yet, here we are, looking back across deep time.